As I mentioned in the previous episode, besides being the universal solvent, water has many other unique properties. For instance, it is the only substance found in nature that can exist in 3 different states: liquid, solid, and gas. Although under the same conditions of temperature and pressure, both its components are invisible to our physical senses. Actually, for water's components to become visible in their liquid form at standard atmospheric pressure, they both have to be cooled down way below 0 degrees Celsius. Hydrogen becomes liquid at about -253 degrees Celsius, while oxygen at about -183 degrees Celsius. It is considered common knowledge that water boils at 100 degrees Celsius or 212 degrees Fahrenheit. However, this temperature is valid only at sea level. As you probably remember from physics classes, the state of matter is strongly related to temperature and pressure. Near the lowest temperature theoretically possible, all substances exist as a solid. Generally, as the temperature increases or the pressure is decreasing, the substance reaches the temperature at which starts to change its state from solid to liquid. If we keep increasing the temperature or decreasing the pressure, the substance turns into gas. The boiling point of water decreases by about 1 degree Celsius for every 300 meters we go up. Thus, on top of Mount Everest, with its peak located at 8,848 meters above sea level, water will boil at about 69 degrees instead of 100 degrees Celsius. Conversely, deep in the oceans, near hydrothermal vents, water can reach temperatures of hundreds of degrees Celsius and still remain liquid. In nature, water likes to break many well-established principles of physics. For instance, it can change its state from gas to solid without going through the transitional liquid phase. The process is called deposition and occurs in the formation of snow and clouds at high altitudes, when water turns into frost on the windows, or when it comes in contact with a metallic surface. Water can skip the transitional liquid state even the other way around, changing its phase from solid directly to gas. The process is called sublimation and is encountered in the winter season when snow and ice evaporate or sublime without melting. This property is used by the food industry when preparing freeze-dried foods. The frozen solid food is placed inside a vacuum chamber where the pressure is decreased at roughly the equivalent to the air pressure 75 kilometers above the surface of the earth. Then, a little heat is added to encourage the ice to leave the food. The low air pressure combined with the added heat causes the solid ice to go straight to water vapor without actually melting, leaving thus the structure and natural pores in the food intact. Another interesting phenomenon is called supercooling. If you live in an area where the environment temperature is well below 0 degrees Celsius, or if you drive through such an area, if you take a bottle of water outside, just by shaking the bottle, water will freeze almost instantly. You can experiment even in your kitchen by placing a bottle of water in the freezer for about 2 hours, then taking the bottle out carefully, without shaking it, and pouring the water on a chilled surface. For best results, water must be as clean as possible, free of impurities. Another extremely counterintuitive phenomenon is that hot water freezes faster than cold water. The phenomenon was known since antiquity. In Meteorologica, composed in circa 330 BCE, Aristotle wrote that the fact that the water has previously been warmed contributes to its freezing quickly, for so it cools sooner. Hence many people, when they want to cool hot water quickly, begin by putting it in the sun. The phenomenon caught the scientists' attention in 1969 after a young Tanzanian schoolboy noticed that if he would place hot ice cream mix into the freezer, it would freeze more quickly than the cooled ice cream mix of his classmates. Usually, any substance contracts when cooled. But water does the opposite, it expands. Also, the solid form of most substances is denser than the liquid phase, causing the block of solid to sink in their own liquid. Water does, again, the opposite. Ice floats on top of the liquid water instead of sinking. Scientists call these properties anomalies because they defy the well-established laws of physics. However, without these so-called anomalies, life as we know it would not exist, because if ice would sink, instead of floating, it would kill in the process all forms of aquatic life. Water manifests a high heat of vaporization, meaning that it requires huge amounts of heat to change its state from liquid to gas and has the highest heat capacity of all liquids. In other words, water requires tremendous amounts of energy to change its temperature. For instance, in the case of mercury, commonly found in mercury thermometers, the heat capacity is as low as 0.1395 joules. This means that for mercury to change its temperature to 1 degree Celsius, the energy required is not even 0.14 joules. In the case of most commonly used building materials, the heat capacity of glass varies between 0.5 to 0.75 joules. Granite has a heat capacity of 0.79 joules, while asphalt has a heat capacity of 0.92 joules. In the case of wood, the heat capacity increases, varying between 1.2 and 2.9 joules. At standard atmospheric pressure and 25 degrees Celsius, water, although a liquid, has a staggering heat capacity of over 4 joules, and even as ice or steam, the heat capacity is over 2 joules, far higher than most building materials. This high heat capacity makes water invaluable in all industries, being used as a cooling agent from nuclear reactors to the automotive industry. In nature, water's highest heat capacity plays a critical role. It regulates the rate at which the air changes its temperature. That's why the temperature is changing gradually between seasons rather than sudden, and cities located near large bodies of water, such as oceans, seas, or lakes, tend to have less change of temperature than inland cities. Moreover, according to the experts from NASA's Jet Propulsion Laboratory, it turns out the oceans can absorb 1,000 times the amount of heat as the atmosphere without really changing their temperature all that much. And 80 to 90% of the heat from global warming is actually going into the oceans. The relationship between water and temperature can be noticed on all levels. Covered with over 70% water, our blue planet is located in the so-called Goldilocks zone, the habitable zone around a star, where the temperature is just right, not too hot and not too cold, for liquid water to exist. All organic life and health are influenced by very subtle differences in temperature, and we're talking about variations as small as 0.1 to 1 degrees Celsius. Humans, plants, animals, and even viruses and bacteria, they're all sensitive to temperature changes. As you already saw in the first episode of this series, all the major internal organs and fluids are made up of water. As humans, we can survive only in a very narrow band of temperatures. If any changes occur inside the body or in the surroundings, the body will exchange heat with the environment because it has to keep a constant core temperature of about 36 to 37 degrees Celsius, even though the skin is only 0.5 to 4 millimeters thick. Even without suffering from a disease, every person begins to sweat if the body's temperature rises by as little as 0.5 degrees Celsius. Conversely, he starts to shiver if the temperature drops with the same amount. And, because the water content differs from individual to individual and varies even during a 24 hours period, the same is the temperature. That's why when you have a fever, you're feeling cold, while all the other persons around you are feeling just fine. Because of this relationship between water and temperature, scientists adopted the joule as the unit for work, heat, and energy, avoiding the calorie as far as possible.